This is the second in a series of resources that look at matrix algebra. We define and provide basic information about matrices. We consider the operations that allow us to manipulate matrices. We discover how to use the row operations to solve a system of equations using matrices. We consider various operations on pairs of matrices, including adding, subtracting, linear combinations, and multiplying. We learn how to find the inverse for a matrix. We discover the determinant for matrices and learn how determinants allow us to solve systems using Cramer's rule. In the previous resource in this series, we discussed the basics of matrices. We saw that matrices provide a method for solving a system of equations without having to write the variables. This becomes important for using computers and other technology to solve problems. But what operations are allowable to manipulate the entries in a matrix? There are three possible row operations. The first is called row swap. It is denoted as R sub I and R sub j with a double-ended arrow between them. Row swap simply rearranges the rows of a matrix. The second row operation is scalar multiplication, in which we multiply all the entries in a row by the same non-zero constant. It is denoted as K times R sub I. The final row operation is linear combination, denoted as K multiplied by R sub I plus R sub j. This operation is much more involved. We multiply each entry in row I by a constant, and then add it to the corresponding entry in row j. One important thing to note is that the entries in row I stay the same. It is only in row j that the numbers change. Let's see some examples. Suppose we have the matrix 3, 18, negative 12, and 21, then 1, 2, negative 3, and 5, then negative 2, 3, negative 4, 6. We want to swap rows 1 and 2. When doing row operations, it is helpful to copy any rows that are not being altered. Since we are swapping rows 1 and 2, we can write in the third row as is. With a row swap, we are simply replacing the numbers in row 1 with the numbers that were originally in row 2, and vice versa. Our new matrix will be 1, 2, negative 3, and 5, then 3, 18, negative 12, and 21, then negative 2, 3, negative 4, and 6. Note that row 3 stays exactly the same. Suppose we start with the same original matrix 3, 18, negative 12, and 21, then 1, 2, negative 3, and 5, then negative 2, 3, negative 4, 6. This time, we want to find the scalar multiplication of 1/3 multiplied by row 1. To complete this row operation, we will multiply each entry in the top row by 1/3. The other two rows stay exactly the same. After multiplying, we are left with the matrix 1, 6, negative 4, and 7, then 1, 2, negative 3, and 5, then negative 2, 3, negative 4, and 6. Now let's try some linear combinations. We will start with the same original matrix, but we want to perform 2 multiplied by row 2 plus row 3. We can write in row 1 right away, since there is no mention of it. When completing a linear combination, the row that is being multiplied by a scalar is our tool that we use to alter the row being added to. The row being multiplied does not change. So for our example, we can copy down row 2. To actually do the linear combination, we multiply each entry in row 2 by 2 and add that product to the number beneath it in row 3. We have 2 times 1 plus negative 2. 2 times 2 plus 3. 2 times negative 3 plus 4. And 2 times 5 plus 6. Completing the calculations, we have the matrix 3, 18, negative 12, and 21. Then 1, 2, negative 3, and 5. Then 0, 7, negative 10, and 11. Let's see one more example of linear combination. Again, we start with the same original matrix, but this time we want to do the linear combination of negative 3 multiplied by row 2 plus row 1. For this linear combination, rows 2 and 3 are not altered. Row 3 is not mentioned, and row 2 is our tool for changing row 1. For row 1, we multiply each element of row 2 by negative 3 and add that to the number originally in row 1. We have negative 3 times 1 plus 3, negative 3 times 2 plus 18, negative 3 times negative 3 plus negative 12, and negative 3 times 5 plus 21. Completing the calculations, we have the matrix 0, 12, negative 3, and 6, then 1, 2, negative 3, and 5, then negative 2, 3, negative 4, and 6. In this resource, we have discussed the 3 row operations. Row swap simply switches all the elements between 2 rows. Scalar multiplication multiplies all the elements of a row by some non-zero constant. In linear combination, we multiply an element from some row and add that to the corresponding element in another row. But why do we do these row operations? Recall that matrices provide a method for solving systems of equations. Row operations will provide the steps we need to complete to find these solutions. How exactly will this work? Stay tuned to the next resource in the series.